Take a look at this sloppily written digit, rendered at a low resolution of 28 by 28 pixels. Your brain has no trouble recognizing it as a 3. For a human, the recognition is effortless. But for a computer, this grid of pixels represents a significant challenge. A standard program lacks the flexibility to interpret these shapes without specific, hard-coded instructions. This diagram reveals why. Underneath the image is a grid of numeric grayscale values, ranging from 0 for black pixels to 1.0 for white. Even when the digit remains a 3, the specific values of each individual pixel change radically from one handwriting sample to the next. This variation makes writing a standard if-then script for recognition nearly impossible. You cannot easily hard-code a set of rules that translates 784 fluctuating numbers into a single correct integer. To handle this complexity, we use a machine learning model, specifically a neural network. Discarding the biological buzzwords, a neural network is a mathematical function defined by a vast array of adjustable parameters. By building this structure from the ground up, we can see exactly how computational logic can be organized to solve visual problems. We start with the basic unit, the neuron. In this context, a neuron is a container that holds a single number. This number is called its activation. It is always a value between 0 and 1, representing how lit up the neuron is. The 28 by 28 grid unrolls into a vertical input layer of 784 neurons. At the opposite end is the output layer, 10 neurons representing the final decision. Between them, we add 2 hidden layers, each containing 16 neurons. We have to ask, what is the specific goal for these hidden layers? What are they actually calculating? Ideally, the network uses hierarchical abstraction. A single neuron in the first hidden layer learns to detect a specific edge, identifying microcomponents like tiny lines. The second hidden layer then combines these micro-edges into larger patterns. For instance, recognizing that specific edges form a loop or a long vertical stroke. Finally, the output layer maps these assembled patterns to a digit. A top loop and a bottom loop result in high activation for the number 8. This strategy of breaking complex data into layers of increasing abstraction is common in other fields, like speech recognition, where raw audio is parsed into distinct sounds, then into syllables, and finally words. This hierarchical design provides a clear objective for the math that follows. To see how a neuron actually detects a pattern, we need to look at the parameters that govern the connections between layers. We assign a weight to every connection between our hidden neuron and the 784 input pixels. These weights are numbers, positive in green, negative in red. Each weight acts as a multiplier. To detect an edge, we give positive weights to pixels in that specific region and negative weights to the surrounding pixels. When we calculate the sum of these weighted values, the result is highest when the target pixels are bright and the surrounding pixels are dark. However, this weighted sum could result in any number, positive or negative. We need a way to control when the neuron becomes active. This is handled by a second parameter, the bias. By adding a negative number, the bias, to our weighted sum, we set a threshold. This ensures the neuron only activates if the sum overcomes the bias. In short, the weights determine what pattern the neuron is looking for, and the bias determines how strong that pattern must be for the neuron to fire. We must ensure the final output of the neuron stays between 0 and 1, regardless of how large the weighted sum plus bias might be. We use an activation function to squish the result into our required range. Historically, we used the sigmoid function, mapping very negative inputs to nearly 0 and positive inputs to nearly 1, with a smooth transition around the center. This S-curve satisfies the biological analogy of a neuron either being inactive or active. However, modern networks typically use a more efficient alternative. That alternative is the rectified linear unit, or ReLU. If the input is negative, the output is exactly 0. If the input is positive, the function simply returns that same value. This activation function is the final step in determining the specific value that is passed forward to the next layer in the network. When we step back and look at the entire network, we see thousands of individual weights and biases. Calculating these one by one would be computationally intensive. Linear algebra provides a method for organizing and speeding up these calculations. Instead of individual connections, we package all input activations into a vector and all weights into a matrix. The entire transition from one layer to the next can then be written as a concise mathematical expression. In this equation, W is our weight matrix, A is our activation vector, B is the bias vector, and sigma is the activation function, like ReLU. This allows the computer to process an entire layer's worth of information using a single matrix vector multiplication. In this specific model, with 2 hidden layers of 16 neurons, there are exactly 13,000 individual weights and biases. These 13,000 parameters are the dials and knobs that define the network's behavior. They are the values that determine if the system can accurately recognize a handwritten 3. We have now defined the structure of the function, but these parameters are currently random. Machine learning is the process of finding the exact settings for these 13,000 numbers, so the network actually solves the problem, which is exactly what we will cover in the next video.